Alright guys, just a little bit more practice on balancing chemical equations. I thought I'd do cellular respiration since that's something that is super common, and that obviously you're doing that right now, right this second, which I think is really cool, and for you to have a little bit of an understanding or a reminder of what that looks like. So we're going to do cellular respiration. That's the process, I suppose, where you take in food, and our food generally, if we can simplify it down, you're taking your food as sugars, and in this case glucose. Okay, so we're going to take in some glucose, and you breathe in oxygen, gas from the atmosphere. And when you do that, your body is really good at taking that glucose and oxygen, and there's a reaction that occurs where it produces carbon dioxide, which is what you breathe out, and water, which is partly what you pee out, right? And you also out of that get energy to do stuff. Right, whatever you need to do, which is kind of cool. So you get the energy extracted from the glucose. This is actually what we call an exothermic reaction, where energy is produced. I'm just going to put energy in there. He's not really part of the balanced equation, but just interesting. So now we've got our word equation. We're going to turn that into a chemical equation. So we need to know what glucose is. So our reactants, glucose and oxygen gas, are our reactants. What are their chemical formulae? I'm going to tell you glucose. If you can remember from maybe previous years, it's got carbon in it, C6, hydrogen, 12 of those, and O6. So that's glucose, C6H12O6. And let's say he's a solid. So that's a molecular compound, a covalently bonded compound. I'm not going to draw him, but there's lots of covalent bonds where these elements are sharing electrons because they're all nonmetals. So just good to remember and check yourself. What type of compound have I got? It's covalent. And oxygen gas. Now we know oxygen gas is O2. Okay. Good little thing to remember about oxygen is, I'm going to draw it in red. When oxygen covalently bonds to itself, because they're nonmetals, he actually forms a double bond. Because remember, he's got 6 valence electrons, then they both need 8, so they actually have to share 2 pairs of electrons. And we can even put on the other electrons that they're not sharing. So if you counted all those up, you'd find 8 electrons around each oxygen. He would be happy. So oxygen always forms a diatomic gas molecule. Diatomic meaning 2 atoms, but he has a double bond. And what do we form? We form carbon dioxide. So carbon dioxide, so carbon, di meaning 2, oxides, oxygens, so carbon dioxide, CO2. Sorry, I forgot to put a little G here for gas. G for gas. So that's carbon dioxide. If you want to know his structure, we've got carbon bonded to an oxygen, but remember oxygen double bonds. And carbon, remember, he actually needs 4 electrons to form a full outer shell, so he needs to form 4 bonds. So you can see that carbon here is forming 1, 2, 3, 4 bonds, and each oxygen is forming 2 like he needs, so that's carbon dioxide. Just a little side note. Plus water, H2O, and that will be, let's say it's a gas for now, could be a liquid, whatever. And you know what water looks like, but I'll put it in anyway. We've got 1 oxygen, 2 hydrogens, and that covalently bonded again. So this is all covalently bonded molecules. There's no ionic compounds here. There's no metals involved, so it's all non-metals, so they'll all be little covalent molecules. Right, so there's our equation that we're going to do. And if you really want to put energy in, you can. There's energy. He's on the side. Don't need to balance him. But now what we need to do is balance this equation. So we need to look at our coefficients. How many of each do we need on each side so that we've conserved our mass and we've balanced our reaction, and that's what occurs in the real world. So we've got to do our little stock take again. We've got carbons, we've got hydrogens, and we've got oxygens. The three of the most important elements for organic chemistry. So carbon, hydrogen, and oxygen on either side, and let's do a bit of a stock take. So we've got 6 carbons at the moment in a glucose molecule. We've got 12 hydrogens, and we've got 6 oxygens here, plus another 2 in this molecule. So we've actually got 8 on the reactant side. On this side, we've got just 1 carbon. We have 2 plus 1 oxygen there, so we've actually got 3 oxygens. And we've got 2 hydrogens, so we've got 2 there. So here's our bit of our stock take. So now what we need to do is to start to look at balancing these, making the numbers on the left side equal the numbers on the right by putting big coefficients in front of elements, or in front of the compounds that will help. So let's leave oxygen till last, because oxygen is in all 4 molecules, he's everywhere. Let's leave hydrogen till second last, and let's do carbon first. So carbon, we've got 6 here, we've only got 1 here. So we're going to need to put a big 6 in front of that. If we do that, that means we end up with 6. We times that by 6, we end up with 6 carbon dioxide molecules, which means we have 6 carbons. It also means that we end up with 6 times 2 of oxygens here. Okay, so we actually end up with 12 oxygens in the carbon dioxide molecule, plus another one, so it ends up with, currently we have 13, which is a big number, but that's okay. We've now balanced our carbons for now, which is good. Next, let's look at our hydrogens, because our hydrogens, again, they're in one molecule here and in one molecule here. Let's balance it before we try and balance oxygens, because oxygen's everywhere, you might screw it up. So we've got 12 hydrogens on this side and we've got 2 on this side. So we're going to need to put a big 6 in front of this, because 2 times, no, I won't do that, but 2 times 6 is 12, so that ends up being 12 hydrogens. So if we're not going to draw all those, but you times the number of waters there by 6, you have 6 water molecules instead of just the 1. That gives us 12 hydrogens, but it also changes the number of oxygens that we have. So we had 6 times 1, so we have 6 oxygens from the water molecules, and we've got 12 oxygens from the carbon dioxide, so we have a total of 12 plus 6, which is 18 oxygens all up, which is cool. So now we've balanced our carbons. Okay, so let's just tick them off, tick, tick. We've balanced our hydrogens, tick, tick. Now we've just got to balance our oxygens. So we've got 8 on this side and we've got 18 on this side. So we need another 10 on this side, right? Another 10 oxygens. Now we could balance it. We could put a number in front of the glucose, because that would increase our oxygens, but that would also increase our carbons and hydrogens, which have already balanced. So we don't want to do that. So let's just leave that guy as a 1. Let's use the oxygen molecule here to balance our oxygens, since if we put a number in front of here, then we're only going to change the number of oxygens, which is good for us right now. So what number needs to go in front of this oxygen molecule to bring the 8 up to an 18? We need an extra 10, right? So let's have a look here. We've got 6 there. So if we put a 6 in front, how does that go? 6 times 2 is 12, plus another 6 is 18. And have a look at that. We're balanced. So we're putting a 6 in front of that oxygen means we have 6 oxygen molecules, that's hard to say, that reacts with 1 glucose molecule to produce 6 carbon dioxide molecules and 6 waters and some energy for you guys to do whatever you want to do. Jump, sing, eat, fall asleep in my class, whatever, right? It produces some energy. So there you go. There's cellular respiration. That's how you balance it. Really cool thing if you're interested. If you're not, you can pause the video right now and stop. But the other really cool thing is that some reactions can actually go backwards, right? Just as a side note here. And so what does the reverse reaction look like? Just as a side note. We've got carbon dioxide plus water plus energy goes backwards to oxygen and glucose. What's that look like? That's actually photosynthesis. That's what plants do, right? So it's actually really cool. One way is cellular respiration. So cellular respiration, that's what we do inside our bodies, or what plants do, I suppose, when they need to grow. And photosynthesis is actually the reaction that goes the other way. Energy comes from the sun, and the plants take up water, and they take in carbon dioxide from the atmosphere, and they turn that into oxygen for us to breathe and glucose for them or for us to eat. So that's kind of cool. Little side note there. But anyway, so we've balanced cellular respiration and photosynthesis all in the same breath. Thanks for watching.